Good morning, everyone. Today, I have to use this means by which I can reach on to you. uh, actually, I'm not physically well, so which is why I will have to go for the teaching of the lesson through this method of teaching. So I hope you will listen well. We are going to start with a new chapter, that is gravitation. Uh, Previously, when we talked about the first week and second week, we did talk about two kind of chapters, that is motion and the force of laws of motion. Now this chapter, that is the gravitation, is very much related with the previous two chapter of motion and the force law of motion. So we will try to speak something about this two chapter here. So normally speaking, when we talk about gravitation, I guess every one of you are having some sort of idea, some rough idea about the gravitation, right? Okay, so here, before speaking about this gravitation or the main course chapter itself, I think it's important for every one of you to know something about the contribution of some of the great scientists. For example, Kepler's. So when people were not even having a single idea about the gravity, it was the great scientists like Copernicus, Galileo, and Kepler's who were researching, who don't have any idea about the gravity, but they have a great interest in astronomy, that they were researching all the planetary motions, which is why they concluded some postulates. So let us go for the first one, that is the Kepler's law. So according to Kepler's, okay, he proposed three postulates, which we used to call as Kepler first, second, and third law. So according to him, his first postulate was, as you can see, this is the planet here, and this is the sun. According to him, the planet, they used to move around, or they used to revolve around the sun in a elliptical way, not in a perfect circles. Understand? Elliptical in the sense, we know the shape of the egg. So this planet, they used to revolve around the sun in a very elliptical way, and he also stressed that the sun is present at one particular focus here, that is at one stationary object here. Is that clear? So that was his first postulate. Now coming on to the second one, he stressed that this planet here is regarding the speed of the planet. This planet, when it is present quite far away, for example, if you can see, this is sun and this is planet here. Now the distance between this sun and planet is quite far, so you can somehow confirm, according to Kepler, is that the speed of the planet at this position or at this position here are very much different according to Kepler's. So according to Kepler, he concluded that the planet, when it is present at this position here or at this position here, the planet tend to go at a slower pace, and this planet, when you can say, when it come across somewhere at this position over here, then this planet, they used to move at a faster speed here. That was his second point. According to him, he confirmed that the planet moves faster when it is near the sun here. For example, if the planet is over here, you can somehow calculate the distance between these two is quite near here. But if this planet is over here, the distance is quite far. So which is why the speed of the planet over here is much more what do you call, slower as compared to the speed over here, right? Okay. Now, if we go for the third one, it is important for us to consider here, that is the speed at the time, that is very, very important here. For example, let's say this planet is moving from this point P3. Can you see this P3 here? From P3 to P4. Is that clear? And when this planet is moving from position P3 to P4, it is covering some amount of distance with some amount of speed. And when it is moving from P3 to P4, it is also taking some amount of time in that, right? Similarly, if you look at this position over here, that is P1 and P2 here, if the planet is moving from P1 to P2, it is also taking some amount of time. and it is also like covering this particular distance at some speed here. Now, according to Kepler's third law, what he concluded is that, according to him, he said that the speed with which this planet moves from P3 to P4 and the speed with which the planet moves from P1 to P2 is same, and the time it takes to cover this, I'm sorry, the time it takes to cover this distance here, this distance and that distance is somehow same, which is why we can conclude area 1 and area 2 is somehow same, right? Okay, so I guess every one of you have understood a little about what Kepler is actually was saying about. He never mentioned anything about the gravity, but instead he was talking about the planetary motions there. So now here, this was a very familiar image for every one of us. Let's say this is Newton, Isaac Newton, and an apple fell on his hat. If we were in his position, we would have eaten the apple. But the genies are genius, and their way of thinkings are quite different. So Newton began to think that why this apple is not moving up, or why this apple is not moving to this direction here. Or he was thinking why this apple is not moving in this direction here. Instead, this apple is moving straight on his head, down in downward nature. So he began to think that why this apple is moving downward, right? There must be some kind of reason behind it. So with this, it was the Newton, okay, who first brought the concept of gravity. He somehow concluded that gravity was the universal force acting between any two objects here. So now here, at the time of the discovery of gravity, Newton has done a lot of work in the laws of motion. We know that force is equal to mass into acceleration. We knew that already, right? So now, if I am going to send this mass to that side here, if I'm going to send this mass to this side here, this mass will go down here below the force. So we have force upon mass is equal to acceleration here, right? So now I have an image here, that is the image of a bigger earth, and let us consider, I don't know what is this, but I will consider this as moon, okay, right? Okay, so now we have two kind of object here, that is object number one, or that is earth, object number two, that is moon here. Now at the time of the what do you call it, the Newton's concept of gravity, he began to think by bringing another concept, that is the apple falling down, right? Apple falling down. He began to think that why this particular earth is not moving up instead of this apple falling down here. So relating this particular concept with what we had learned over here, according to this particular equation, we knew that acceleration is directly proportional to f, but acceleration is inversely. That means it is divided by mass here. That means acceleration is inversely proportional to mass here. That means uh, the next one here. That means acceleration is inversely proportional to mass, which confirms that whenever there is a huge mass, for example, this is the Earth here. If you compare the mass of the Earth and apple, we can somehow say that the mass of the apple is what do you call very very much like very we cannot like somehow calculate, right? If you compare it to the mass of the Earth. So over here the mass is so high that there is a very less amount of acceleration on moving top here, on moving upward in towards the apple. If the mass is very lesser here, for example, this mass is very less, very less if you compare to that Earth, then there will be more kind of acceleration, which is why apple is always falling down. But instead, this Earth is not moving toward the apple here. Is that clear? Yeah. So the various kind of observation made by Newton started with the falling of an apple on his head, And it was in 1687 that Newton gave the universal law of gravitation. So, according to him, he concluded that the gravity can occur between two objects here. For example, in this case here, I have Earth and Moon here. And since there are like two objects here, and these two objects are also having masses here, right? Okay. So, according to Newton, he concluded that uh, the gravitation force means between the Earth and the Moon, there is a kind of like a gravitational force. How strong this gravitational force is is dependent upon the mass of this object and that object over here. Let's say instead of this Earth and Moon, if you have a smaller, what do you call, objects like ball, let's say tennis ball, which is at a similar distance to that of Moon and Earth, then we can somehow conclude that uh, what do you call the gravitational force between two tennis ball is much more smaller to that of Moon and Earth here. Understand? So with this Newton first point was that if the object is having more mass, that is more mass here, then the gravitational force is more. If the object is having a lesser mass, then it is having a lesser gravitational force. Now, these two objects, they are separated by each other through some distance here. For example, from Moon to Earth, there is distance, and Earth to Moon, there are distance, but both the distance are same, right? So, Newton secondly concluded that if the two objects are quite closer to each other, then the gravitational force is stronger. If the two objects are quite far away, for example, there is a very small amount of distance in this picture here, but if I bring this particular moon at this position over here, and if I bring this particular earth to that position over here, then we can conclude that if the distance is more, then the gravitation force is much more lesser. That means it acts in an opposite way, which is why we conclude that the gravitational force is inversely proportional to the distance between the object here is over here, right? So this was the two postulate given by Newton. So with this, he gave one formula here, that is this is m. This is the one of the mass of the object, and this is another mass of the object, that is m. We in our textbook we used to write m1 and m2, right? Okay, it doesn't matter whether you write capital R or small m. So this is r square here. R square. Why we are writing r square is like this here. For example, from Moon to Earth, there is a gravitational force. From Earth to Moon, there is a gravitational force. As you can see, there are two kind of distance here, but both the distance are same. As we are measuring the distance, we can somehow conclude that both the distance are same between each other, right? So which is why there is two kind of distance here. One is from Moon to Earth, other is from Earth to Moon. Uh, Normally we used to consider in the same case, but in this case we used to write r square here. Now this is proportional. Now whenever we are writing an equal to, there will be what do you call? There will be a present of a new constant value, that is capital G, whose value is also 6.67 into 10 to the power minus 11 Newton meter square divided by kg square. And this G is also referred to as the constant of proportionality, right? Okay. So this Newton law of universal gravitation is also referred to as the inverse square law, right? Inverse square law. Okay. Now, why this universal law of gravitation is important? Because with the understanding of this universal law of gravitation, we came to understand that the force that binds means that if there is no gravitational force, then let's say all the objects or the matters that are on the earth, it will fly away at some point. Okay, that means we can walk, we won't be able to walk if there is no gravitational force. And the second one is motion of planet and moon around the earth. That means the planets and moons, they are revolving around the Earth, but they are not going forever. They just revolve around the Earth, and this happens. Why? Because there is a kind of attraction, the attractive force between the two, what do you call, planets here. Now the third one is quite important here. That is tides at sea. Tide means in our Tibetan language we used to say "chubalapliya." Okay, tides at sea. Now, how this happens here? For example, I have a picture here. A man is grabbing a glass of water, or if the man is not grabbing this glass of water, we will see the water present in this glass is not going to move. So if the moment man started to touch the glass, the water in this glass is going to change. It creates a waves, or you can say a small tides here. In a similar way, our earth, as I had shown you before here, our earth is also experiencing some gravitational force from moon, and this earth is having 70% with water here. Whenever there is a small kind of gravitational force, the earth try to drag, okay, it tries, no, I mean the moon, they tries to pull earth. When moon tries to pull the earth towards itself, there is a little amount of movement in the water, and that movement is what we used to call as tide. So whenever there is a presence of huge tide in the water, we can somehow conclude that the moon is present quite near to us. Now let us imagine, okay, there are some planets which have like 12 moons. Now my question to you is, what will happen if there are, for example, we have like one moon right now. If we have the presence of like 12 moon, what will happen? Can you think of like two positive point, two negative point regarding this? So thank you very much. I will see you in the next class, maybe in a classroom. I shall see you, every one of you. So thank you very much for you listening very well. Thank you, all of you.